Hi everyone. This is NLP Corgi. Today's deep dive is about the paper from Shanghai University of Finance and Economics, QuantaAlpha, an evolutionary framework for LLM-driven alpha mining. Financial markets are messy. They're high-dimensional, full of noise, and constantly changing their behavior over time. Quant investors rely on alpha factors, predictive signals, to find an edge, but those signals can decay quickly when the market regime shifts. Recently, large language models and agent frameworks have started to automate factor research, from hypothesis generation to backtesting, but even these advanced systems still struggle with stability, control, and long-term robustness. Existing LLM-based alpha agents typically iterate in a loop, propose a hypothesis, write code, backtest, and tweak. In practice, three problems show up. First, controllability is fragile. Noisy backtests can push the model towards spurious correlations, drifting away from the original economic story. Second, trust is limited. Many systems regenerate factors from scratch each round, without a clear lineage of what worked and why. Third, exploration is narrow. They tend to stay near their initial ideas, producing crowded, redundant factors that don't generalize well. QuantaAlpha takes a different view. Instead of treating each factor as an isolated object, it treats the entire research process as a trajectory. From hypothesis, to symbolic factor, to code, to backtest. These trajectories are then evolved using ideas from evolutionary algorithms, mutation to locally repair weak steps, and crossover to recombine strong segments from different runs. Throughout, QuantaAlpha enforces semantic consistency between hypothesis, formula, and code, and actively controls complexity and redundancy, so the factor zoo stays simple, diverse, and interpretable. Here's the full QuantaAlpha pipeline. It starts with diversified planning. The system proposes multiple, complementary research directions, such as different time horizons, signal sources, or mechanism types. Next, in factor realization, each hypothesis is turned into a symbolic expression over a standardized operator library, parsed into an abstract syntax tree, and then compiled into executable code. Consistency checks and structural constraints keep everything aligned and manageable. On top of these evaluated trajectories, QuantaAlpha runs self-evolution, mutation to fix weak steps, and crossover to recombine strong patterns. Over iterations, it maintains a final factor pool, a curated set of validated, non-redundant factors. The process starts with an idea agent that proposes market hypotheses grounded in current conditions, financial theory, and optional user seeds. A factor agent then turns each hypothesis into a symbolic factor expression using a fixed operator library, things like rolling means, ranks, and technical indicators. This expression is parsed into an abstract syntax tree, which makes the structure explicit. Leaves are raw features like price and volume, and internal nodes are operators. Only after this symbolic form is validated does the system compile it into executable code, repairing implementation issues while preserving the intended semantics. A key risk in automated factor generation is semantic drift. The code no longer matches the economic idea. QuantaAlpha addresses this with an LLM-based verifier that checks consistency at two levels. First, it compares the hypothesis, the structured description, and the symbolic expression to ensure they tell the same story. Second, it checks that the compiled code faithfully implements the symbolic formula. If any link fails, the offending component is rewritten within a fixed retry budget. This keeps the entire pipeline anchored to the original economic mechanism. QuantaAlpha doesn't just generate any factor that backtests well. It explicitly penalizes complexity, using a score that combines symbolic length, the number of free parameters like window sizes, and how many base features are used. It also measures redundancy structurally. It compares abstract syntax trees to detect large shared subtrees with existing factors. If a candidate is too complex or too similar to what's already in the zoo, it's rejected and rewritten. This keeps the factor set parsimonious and reduces crowding, which is crucial for robustness in live trading. Once a factor is executable, QuantaAlpha evaluates it in a standardized backtesting environment. It looks at predictive power using information coefficient and rank IC, along with their information ratios to capture stability. It also measures strategy-level performance under a fixed trading rule. Annualized excess return, information ratio, maximum drawdown, and Kalmar ratio. The main development and selection happen on the CSI 300 universe, and then the resulting factors are tested zero-shot on CSI 500 and the S&P 500 to probe robustness under market shifts. Conceptually, QuantaAlpha treats each full mining run as a trajectory, a sequence of states and actions, from initial context to final evaluated factor. The reward of a trajectory is the factor's predictive performance minus a regularization term for complexity and redundancy. The goal is to learn a trajectory generation mechanism that maximizes expected terminal reward. Crucially, evolution happens at the trajectory level, instead of randomly regenerating factors from noisy feedback. QuantaAlpha edits and recombines entire research paths, preserving useful structure and experience. The first evolutionary step is diversified planning. Given user-provided seeds or high-level ideas, an initialization agent proposes a set of initial hypotheses that are deliberately different from each other. They may focus on price versus volume, short-term versus long-term horizons, or momentum versus mean reversion and regime condition logic. Each hypothesis is then turned into a full trajectory and evaluated. This broad initial coverage helps the later mutation and crossover steps explore multiple promising regions of the hypothesis space, instead of overfitting to one narrow neighborhood. Mutation in QuantaAlpha is not random. Given a trajectory, the system first performs self-reflection to identify which decision step most likely caused poor performance. Maybe the hypothesis was too narrow or the factor expression overfit. It then rewrites only that local segment, such as adjusting the timescale, adding a regime condition, or simplifying the formula. The earlier steps are kept fixed, and the later steps are regenerated conditioned on this prefix to maintain coherence. This targeted repair lets the system escape bad local choices while preserving what already works. Crossover focuses on reusing what has already been validated. From the pool of trajectories, QuantaAlpha selects high-reward parents and identifies which segments consistently contribute to good outcomes, such as robust hypothesis templates, reliable factor construction motifs, or effective repair strategies. It then recombines these segments into new child trajectories. This is similar to how human quants mix and match ideas from different successful strategies. The result is a new trajectory with a clear lineage. You can trace which parts came from which parent and why they were chosen. On the CSI 300 universe, QuantaAlpha outperforms a wide range of baselines. Traditional machine learning models, deep time series models, classical factor libraries like Alpha 158 and Alpha 360, and state-of-the-art LLM-based agents such as RD Agent and Alpha Agent. Using GPT 5.2 as the backbone, QuantaAlpha reaches an information coefficient of about 0.15, an annualized excess return of nearly 28%, and a maximum drawdown under 8%. Compared to RD Agent, it delivers much higher IC and ARR with lower drawdown. Even relative to Alpha Agent, which already uses generation stage regularization, QuantaAlpha adds a sizable boost in both predictive power and risk-adjusted performance. To understand where the improvements come from, the authors ablate key components. When they remove diversified planning, predictive metrics barely change, but strategy performance drops. Annualized return falls and drawdown rises. This shows that broad initialization mainly stabilizes the search frontier. Removing mutation has the largest impact on predictive power and returns, confirming that targeted trajectory repair is the main engine of exploration and improvement. Removing crossover also hurts, though less dramatically, indicating that recombining validated segments improves efficiency and stability by reusing good patterns instead of rediscovering them from scratch. The authors also test what happens if they relax the generation time gates. Disabling semantic consistency checks, complexity regularization, or redundancy filtering each leads to worse predictive and strategy metrics. Complexity control stands out. Without it, annualized return drops sharply and maximum drawdown increases, suggesting that overly intricate formulas overfit and fail in live-like conditions. Redundancy control helps avoid factor crowding, and consistency checks keep the economic story aligned with the implementation. When all three are removed, performance degrades the most, showing that these controls are complementary and jointly necessary for reliable factor generation. A critical test is whether factors survive outside their training environment. QuantaAlpha's factors, mined and selected on CSI 300, are deployed directly, without retraining, on CSI 500 and the S&P 500. Over roughly 4 years, QuantaAlpha achieves about 160% cumulative excess return on CSI 500 and around 137% on the S&P 500, clearly outperforming competing methods. Notably, when market microstructure and volatility regimes shift around late 2023, many baselines stagnate, while QuantaAlpha's factor portfolio continues to climb. This suggests that the discovered signals capture more structural, transferable patterns rather than overfitting to one market's history. The authors zoom in on alpha decay during a major regime shift in the CSI 300, around 2023. Before 2023, large-cap core assets and stable trends made classical momentum and mean reversion work well. In 2023, leadership rotates to small caps and thematic names, with noisier intraday behavior and more overnight gaps. Many baselines see their IC and rank IC collapse under this new regime. QuantaAlpha, by contrast, maintains strong predictability. Its factor library emphasizes structural signals like overnight gap behavior, volatility clustering, and trend continuation conditioned on liquidity quality. These are less tied to a specific style and therefore generalize better across regimes. A detailed, factor-level analysis compares QuantaAlpha to Alpha Agent in 2023. QuantaAlpha's strongest factors focus on overnight gaps relative to recent ranges, how intraday price action accepts or rejects those gaps, and whether that behavior is backed by abnormal volume. It also uses range-based volatility structure and trend quality filters that require low residual noise and orderly liquidity absorption. Alpha Agent's best factors lean more on exhaustion and climax-style reversals, and its weaker ones often bottom fish in unstable liquidity regimes. Statistically, QuantaAlpha has higher coverage, a larger share of factors with positive rank IC, and a much heavier right tail, meaning more genuinely strong signals survive the regime change. Tracking the evolution over multiple rounds reveals how the system learns. QuantaAlpha's average IC improves rapidly in the first few iterations, and then stabilizes at a high plateau. Importantly, the distribution of IC values retains a healthy spread, indicating ongoing diversity in the factor candidates rather than collapsing to a narrow family. Compared to RD Agent and Alpha Agent, QuantaAlpha consistently achieves higher IC at every iteration. This suggests that trajectory-level mutation and crossover are more sample-efficient at turning early exploration into a stable population of predictive factors. A concrete case study shows how a factor evolves over 5 iterations. The process begins with a straightforward, short-term reversal idea, filtered by volatility. Mutation then introduces a more complex volatility-weighted momentum structure, which improves signal strength but hurts generalization. Subsequent iterations simplify the expression into a cleaner linear form, improving drawdown and stability. Later crossover steps bring in complementary behavioral information, such as distinguishing institutional from retail-driven flows. Throughout, a global factor pool is maintained with redundancy constraints, and performance continues to improve until around the 15th iteration, after which returns to additional complexity start to diminish. Evolution can't run forever without cost. By tracking the performance of the factor pool over many iterations, the authors find that both return and risk metrics improve steadily up to around the 11th or 12th iteration. After that, adding more factors tends to introduce redundancy and noise, which can weaken robustness and worsen drawdowns. In their setup, a pool of roughly 350 factors around iteration 11-12 offers the best balance between return and risk. This suggests that evolutionary alpha mining benefits from a principled stopping rule, rather than blindly maximizing the number of iterations or factors. Stepping back, QuantaAlpha contributes 3 main ideas. First, it treats alpha mining as trajectory optimization, using mutation and crossover to evolve entire research workflows rather than isolated formulas. Second, it grounds factor construction in symbolic representations with strict consistency, complexity, and redundancy controls, which greatly improves controllability and trust. Third, it demonstrates strong empirical robustness, better predictive and strategy performance on CSI 300, effective zero-shot transfer to CSI 500 and S&P 500, and resilience to regime shifts like the 2023 style rotation. The resulting factors are not just profitable in backtests, they're interpretable, diverse, and traceable. The authors also acknowledge limitations. The current experiments focus on equity indices like CSI 300, CSI 500, and the S&P 500. Extending to multi-asset and cross-market settings is an open direction. The evolution process, while robust, is not yet explicitly regime-aware. It doesn't dynamically adapt its operators based on detected market states, and the agentic discovery loop is still somewhat decoupled from downstream portfolio construction and risk management. Future work aims to close these gaps, and more broadly, to apply agentic evolution to other high-noise, non-stationary domains beyond finance.